Hey everybody, we're going to run through recovery real quick here. Um, One of the PowerPoints in Blackboard is giving me some sort of corrupt error, so you won't be able to open that. But I'll try to get that fixed. But in the meantime, we can still go through this. So I'm going to pull up this one because it has a lot of the same slides in it, and I'll try to upload it to Blackboard. So first of all, why do we recover? Why do we have to recover refrigerant in the first place? So if you go to your book, I think this is in, let's see, chapter 9, I believe. The PowerPoint for the book really doesn't go into a lot of, no, it's not that one. Yeah, it is. So it goes into more of the EPA side of it. So why do we recover in the first place? Well, for one, you don't want to just release refrigerant into the atmosphere because it has harmful properties. Some of it does, most of it does that we work with. Um, it has ozone depletion potential. Some of the older refrigerants that have the chlorine in them. So if you're studying for your EPA test, or if you remember from the EPA test, anything with chlorine, that's the ozone depleting uh, chemical. And then some of the newer refrigerants did away with the chlorine. So you had CFCs, chlorofluorocarbons, HCFCs, hydrochlorofluorocarbons, and then you had HFCs like 410A, which are um, hydrofluorocarbons. So they did away with the chlorine for the ozone depletion part, but what they're finding from that is that we still have the potential to create a global warming factor. Whether you agree with that or not, it is what it is. I know that's kind of up for debate, but that's the regulations and that's what they're based on. So you got ODP and GWP. Um, so 410A has it doesn't have much ozone depletion potential, but it still does have a high global warming factor. Um, so that's why they're probably going to be changing from that. I'd say in the next 20 years, I feel like they'll go away from that as well. So don't be surprised whenever there's another change on the horizon. But you're already going to start seeing more about flammable refrigerants, things that are safe for the environment, safe to use. They're already in use in a lot of places. They're already in use here in smaller equipment. So that's probably coming down the pike sooner than later. But for now, this is what we have. So not going to spend a ton of time on this, but you can look through this yourself. This more talks about that end of it, the EPA end of it. And then it goes into the three R's: recovery, recycling, and reclaiming. So recovery is really the only one that we're going to do out in the field. Recycling you could do if you took it back to your shop or something and had a set of filters, but I mean you're not just running it through a filter dryer. Like this is oil separation, multiple passes through multiple filters. So, you could do it. I've seen guys that have it set up in their shop to clean up refrigerant to recycle it, but most guys aren't doing that. So mostly what we're doing is recovering. And then to reclaim, you're actually sending it back to the factory, back to a lab, and they're actually taking it back to brand new specifications. So I'm not going to spend a ton more time on the textbook um, portion because it kind of doesn't cover what I want to cover. All right, so the main thing you need to remember on refrigerant recovery is how to do it, how to hook up your setup in the first place. It's kind of like pulling a vacuum. Uh, there's different ways to do it. Different people have different ways, but there's ways that you can make your setup a little more efficient, a little more effective, quicker. The old way, the way that it used to be done before the pumps got a lot better than they are now, is we would pull strictly as vapor because the pumps wouldn't handle liquid. And so that wasn't really a problem in R22 because R22 is not a blended refrigerant. But 410A and most of these modern refrigerants we're working with are blended, which means they're made up of multiple refrigerants that are combined that all have different properties. So you have to put them in as a liquid. Same way with charging. When we get into charging, I'll say that again. So when you're putting them in or pulling them out, whatever, you have to handle them as a liquid, because if you don't, you could do what they call is fraction. You could do fractionization, which is basically breaking down the parts of the refrigerant that would be boiled off at certain temperatures, and there could be parts of it that's still not completely vapor, or so you've got an improper blend. Whereas if you pull the liquid or you take the liquid out, you're going to get the whole mix. So you want to try to take it out as a liquid. um, so this slide is actually a little bit dated, but it still serves a purpose. So on your refrigerant recovery machine, it's got an inlet and an outlet. It's very similar to your HVAC system, really. It's got a suction and a discharge. And so inside of there, some of them actually have a little small compressor and condenser, and some of them are just using more of a pump setup. So depending on the type of machine that you have, um, I'm pretty fond of the Appion G5 because they handle liquid refrigerant really well. I've also got a yellow jacket that I use personally that I like that can handle liquid or vapor. So um, a good pump's going to cost you some money, but it's going to save you a lot of time. All right. So if you're pulling vapor, obviously that's a slow process. The only reason now that I could see pulling vapor, or in a time that I've actually had to pull vapor because I thought it was a good process, or it was needed at the time, was we actually had a chiller that had several 100 pounds of refrigerant in it, and the refrigerant oil was, well, for one, we were trying to separate the oil because there was too much oil in the system, and it was acidic as well. So we were trying to get the refrigerant off of the oil, and it was R22, so we didn't have to worry about fractionization. So what we ended up doing is we hooked up our system to pull vapor, and then we put an inline condenser in it. So they make a thing called a coax coil, and I think it actually shows that in this manual. I'm gonna show you later. Um, but essentially, you run water through a coil. It's just water cooling that vapor and cooling it down, condensing it. So then you drop it into the tank as a condensed liquid, which keeps the pressure of your tank down and allows you to be able to recover it. So, and it speeds up recovery too. So the reason we did that was we thought if we could do that, we could separate more of the refrigerant from the oil, because a lot of that oil in that system, because of some other factors, had gotten transferred into different parts of the chiller. Because we had an issue. And so we were trying to separate the refrigerant from the oil as best we could so that we could drain the oil out. So that was kind of a special case. So you could do that in a case where you have R22, but 410A, anything like that that's a blend, you're going to have to do something else. You're going to have to get the liquid out. Push pull, I'm going to go into more of this here in a minute, but a push pull setup is actually where you are using the machine to pressurize the system, and then you're using the system pressure. You're wanting the system pressure to be higher than the tank pressure so that the refrigerant will just naturally flow into the tank. So you're not actually pulling it out and then pushing it into the tank. You're actually doing the opposite. You're pulling off of the top of the tank. So if you'll notice here, they're pulling vapor off the top, pressurizing the system, and then hooking a line on the liquid side back to the tank and allowing the system pressure to build above the tank pressure so it naturally flows in. It's actually a really effective way to do it. It's a good it's high speed. It's pretty good if you're doing a large amount of refrigerant. All right, so here's our Appion. This is the ones we use in lab, or mostly. There's some other ones out there now that are very similar. Fieldpiece makes a new one. but these are really good. You'll notice it has throttling valves on the inlet and the outlet, and there's also a screen inside of the inlet to protect it from any dirt and debris. So sometimes those can get clogged up, so it's not a bad idea to check that screen. You don't want to remove the screen, you just want to check it and clean it. All right, so another way that you can recover, especially if you don't have electricity present, you don't have maybe a lot of refrigerant to move, or maybe you got a system that's overcharged. And so you're trying to just remove a little bit of refrigerant, and you don't want to go to the trouble of getting out your tank and, I mean, getting out your machine and all that. Maybe it's on a roof or something. You don't have good access to electricity, or you just don't want to drag everything up there. You can, if you have an empty refrigerant tank, you can pull a vacuum on the tank, put it under a negative pressure, and then allow the liquid refrigerant to naturally flow in. And you can get a lot that way. And if you got the system running, you can do a passive recovery, which is actually using the system pressure to increase the outlet pressure and then just push it into the tank. So you can get a lot of refrigerant that way, but you can't get the system empty. So if you're trying to completely remove everything, you're not going to be able to do that. But if you're trying to remove a few pounds, maybe because you think you're overcharged or something, then that's a good way to do it. On your recovery cylinders, this is actually really important information here. WC on this tank, it'll show you water capacity. Now, water capacity obviously is like if this thing were completely full of water, this is how much water it would hold. So refrigerant is a little different than water. Normally we're gonna fill that no more than 80% of its water capacity, of its WC, because that refrigerant, when it's put in as a liquid, once that tank has a chance to heat up and that refrigerant has a chance to heat up, or maybe it's in the back of a truck and it gets warmer, it's going to start to raise pressure, start to boil off more. You get more vapor, and so you're going to build a lot of pressure in that tank. So if you completely fill that up, you don't have anywhere for it to expand to. So you want to fill it to 80%. So you got to calculate that. The tare weight, TW, that's the weight of the tank when it's empty. So if you're unsure if there's any refrigerant or how much refrigerant's in a tank, you can compare the tare weight to the actual weight and then just subtract that. Every tank is different, so they're not always 17.1 in this case. Um, every tank is different. So for that particular tank, this is what it weighs when it's empty. And then if you have 5 pounds more than that, then you could assume that there's 5 pounds of refrigerant in the tank. Now, obviously, you would want to do this without your gauges and all that stuff hooked up, because those will add weight to the tank. So this is just your empty tank weight. All right, so that's that. I'm going to pull up, if I can find it here. I'm going to pull up this G5 manual, G5 Twin. This is that Appion manual, because it's actually got some really good diagrams in it. And I'm handing you this in class, so you'll have this. You'll have access to this. It'll be on Blackboard as well. But it actually has some pretty good, clear diagrams. So one thing they recommend to do, it's not required, but it's a good practice to do, is to put an inline filter dryer on. Now, in order to do that, obviously you're going to have another hose, but you can put an inline filter dryer on, and that just protects your pump, and it also kind of conditions your refrigerant before you put it into your tank. So you're pulling out, in this case, you're pulling B and A. It says valve core removal tools are optional. So we use valve core removal tools for vacuum to speed up the vacuum process, but we can also use those for refrigerant recovery because it's going to speed it up too. And it also keeps it from breaking, from metering, because sometimes as it comes out as a liquid and it goes through that Schrader, comes into our hoses, it can flash right there, and that can cause some of it to flash off, and that can raise your pressure. So one of your main purposes, or one of your main things you need to keep in mind to keep your vacuum efficient, keep it running, or your recovery efficient, to run it as quick as you can and not damage your pump, is you got to keep your tank pressure low. So that's why condensing that and keeping that as a liquid is the best way to do it. If you start putting it in as a vapor, your tank's going to get really, really hot. And as it gets hot, it's going to build back pressure, and then your system's going to have your machine's going to have trouble pumping against it. Plus, it could be a danger issue. I mean, most time it's not going to be, but it could be. So you want to keep that tank cool as you can. All right, so it shows you the process of that. So basically, you're just hooking an inlet. You're hooking your red and your blue to your liquid and vapor line. You're hooking your yellow line to the inlet of your pump, and then another extra hose. So you got to have an extra hose, fourth hose, to the outlet of your pump. Now, there is some discrepancy as to what port you hook this to. Appion says hook it to the vapor line. Okay, they do say to improve tank cooling, start with the recovery cylinder upside down and flip it right side up near the end of the vapor recovery. So what you're doing mainly is you're pulling out the liquid refrigerant, and then when you get to the end, once you get the system almost empty, there will be some vapor. So one rule of thumb, or one school of thought, says that you can hook it to the liquid line and push it through the liquid line. Now, the problem with that is you've got a dip tube that goes all the way down to the bottom of this, and you can kind of see it in this picture here. So your liquid line has a dip tube that goes down and pulls the liquid off the top, so that when you're pulling it back out as a liquid, you don't have to flip the tank upside down. So the liquid side goes to the bottom. Well, you've got to push that refrigerant through your hoses and then through that little tube down into the liquid, so your pressure is going to build up a whole lot more, especially if you're moving a lot of refrigerant. So what they recommend to do is to put it in the vapor side, which is not the way I've always done it, but maybe you need to consider. But then to increase the speed and to keep the tank cooler, especially if you're moving a lot of refrigerant, flip that tank upside down. So that way you're still pushing it into the liquid and you're not flashing off, but you're not having to push it through that dip tube. So that's the thought behind that. And then you're just going to open everything up. You've got your throttle valves here on your pump. You'll want to start with those closed, and then you'll open those up, open your outlet, and then you'll probably need to open your inlet kind of slow. If you hear your pump kind of banging and knocking, then you'll want to slow it down because you're getting too much liquid. So it can get too much and it can kick the pump off. And you want to make sure everything downstream of the pump is open. So your tank's open, your hoses are open, your outlet valve is open. Because if you start pushing against a closed valve, that's going to create a pressure increase, and it's going to cause the pump to kick off or cause damage. The next one is now they're calling this like a high-speed liquid. This is actually a pretty cool little setup. So they're pulling only out of the liquid line in this one, and through the machine and pushing into the liquid port. And then as the tank pressure raises, there's going to be vapor on the top that's going to increase. So they're pushing that vapor back in to the vapor side. So they're increasing the pressure of their machine or their system. So the recovery, this allows for the fastest possible direct liquid recovery machines. But then you got to pull the vapor out after you're done. So that's another way to do it. Kind of a neat setup there. So I've never done it that way, but it's pretty cool. Standard with inline cooling, kind of similar to the other one, only you're pulling vapor and liquid, and you're using that vapor to actually cool down the liquid refrigerant, looks like. So I don't know, that one looks a little bit involved, a little different. The next one, push pull. So this is one that I have used quite a bit, especially on larger systems, and it's really effective. So we already kind of went through it a little bit, but I'll show you here how it looks. You hook up your vapor, you hook up your liquid. Your liquid is going into your tank. So system pressure from the system itself should be larger than the tank pressure. And that liquid refrigerant is just going to dump into the tank. But the reason it's doing that is because they're pulling the vapor off the top, which reduces the pressure of the tank, through the inlet of the recovery machine, through the outlet of the recovery machine, back into the vapor side. So you're increasing your vapor, which is increasing your system pressure. You're pulling the vapor off the tank, which is decreasing the tank pressure. So you're creating this big imbalance. So your system pressure is going up, your tank pressure is going down, and as a result, this liquid refrigerant is going to freely flow from one side to the other. So that's actually a pretty cool little diagram. Another thing, here's that coax I was talking about. So it's a little hard to tell what that actually is right here, but um, you can get this one's not a coax. It looks like it's looks like this one is one you would just put in water. So you could coil some refrigerant tubing, maybe 3/8 or something like that, 5/16. They're saying 5/16. Coil it around and put your access fittings on the end of it. And then what you're going to do is you're going to actually take that, um, and I'm assuming they're going to tell you to put it in like a bucket of water or ice water, so it just creates a condenser. That's one way to do it. Another way to do it, or in addition to that, so yeah, here you go. So they're actually putting that in um, ice water or in cold water to transfer some of that heat, which cools down your refrigerant, which decreases your tank pressure. You're not going to need to do all this for some residential system that has 10 pounds of refrigerant in it. But if you're removing large amounts of refrigerant, this could be a really big time saver, and it's going to be a lot safer too. One thing you can do, and I've had to do in the field a little bit, if you're removing several pounds of refrigerant, or if your tank's starting to get kind of full, and so it's building pressure quicker than normal, um, you can pack that tank in ice or in cold water, or even, I've even used just a garden hose to run over top of it a little bit to cool it down and then put it back on my scale. So, I mean, there's a lot of different ways, but basically all you're doing is you're getting the temperature of that tank down so that more of that condenses and you're not sitting there fighting that tank. Because what you're doing is your pump has to overcome whatever pressure the tank is to push it in. And then, as we mentioned, core removal tools are great. Um, because you can take those out and it's going to speed up the process a lot. According to this, it says cores block about 90% of the flow through the access port. So we use core depressors, which they didn't turn around, and as we learned in vacuum or evacuation, um, they block 50% of that. So you got very little refrigerant actually able to move through. So it can take a whole lot longer. Well, if you're only removing a few pounds, it's not a huge deal. But if you're trying to remove, 100 pounds of refrigerant, those core tools are going to be or those cores are going to be in your way. So speed your process up a lot. Just get in the habit of taking those off. And the other thing is, if you're going to be pulling this out at some point in time, if you're using these for your vacuum, you're going to be taking them. You're going to be putting those on anyway. So why not put them on from the get go? Remove your cores, keep them out through the whole process, and then put them in when you're done, when you've charged it back. So um, use shortest length and larger diameter hoses. Now, I don't recommend that you use your vacuum hoses. So hopefully, we're going to use larger diameter vacuum hoses, but this is charging hoses. So you can actually get 3/8 and even greater sized um, hoses, red, yellow, and blue, or whatever. Or you can get some more vacuum hoses even that would work. But I wouldn't use my vacuum hoses for recovery. You could use your gauges, your 1/4 inch hoses like normal, but if you're trying to remove a lot in a short amount of time, larger hoses is going to be a big deal. So when I was at the university, we actually had that chiller I was talking about, and we hooked 1/2 inch hoses. We ordered 1/2 inch hoses special with 1/2 inch fittings on them, which are really large diameter hoses because we had to move a lot of refrigerant, and I mean, that was a game changer because if we'd had to pull it all through our gauges, we'd have never got it out. That's about it for that. So that kind of gives you a little bit of a um, background, and then what I want you to do is to go through that module and look at those videos. So those videos show you some different real life applications. how to recover refrigerant with the compressor running, adjusting the charge, using the compressor or recovery machine, liquid commercial push-pull recovery, and then you got a quiz at the end. So if you could go through that, that'd be great. Knock that out for me, and you'll be good. Thank you all.